want a robot to move like a human, you need to solve actuation. Actuators are the bridge between software and motion, just like our muscles are the bridge between our brain and our body.
Phantom is equipped with low backdriving torque, low inertia, and high bandwidth actuation of over 100 Hz. It comes with very transparent actuation, and we don't need any additional sensors or software to get this compliant behavior.
Our design enables open-loop torque control, resulting in robots that are not only incredibly safe to interact with, but also exceptionally reliable and robust. They're engineered to interact in real-world environments just like we do. This is safety without complexity.
Clean and precise jobs were automated about 20 years ago. They're dangerous and unpredictable environments. Our hardware is designed for harsh, unpredictable places and is adaptable just like people.
AI has already changed the digital world, but to live among us, it needs to move beyond the internet data into the chaos of reality. So what's missing? The ability to reason through our world, just like we do, with an intuitive understanding of physics. We learn that from birth by interacting with the world, but AI doesn't. Methods like reinforcement learning and behavior cloning can learn specific tasks, but they don't handle new situations well. They don't understand how the world works. They just copy behavior or learn by trial and error. Enter latent space models. They simplify this messy real-world data into abstract maps. Think a bit of it as AI building its own understanding of reality, just like our brain does. Deep variational Bayes filters, or DVBFs, take this one step further, learning the laws of motion without being spoon-fed each and every example. DVBFs encode sensory inputs, like a robot's camera or touch sensors, into a latent space, and using Bayesian inference, they update their beliefs about the world as new data comes in, and then encode predictions to act. It's a bit like giving AI a sense of imagination. Unlike behavior cloning or traditional neural networks, DVBFs don't just generalize from data, they understand the why behind action. They need much less data, adapt on the fly, and can predict what's next. For me, that's like AI finally grasping the rules of the game. And
hand. It may look like a hand, it has 4 fingers and a thumb, but it doesn't function like a true hand. To find out why that matters and what the differences even are, I spoke with the robotics engineers here at Foundation. This is Andrea, lead hand mechanical engineer. He knows a lot about hands.
Yeah, so early on I got into the rabbit hole of studying biomechanics in depth. So I bought this anatomy book entirely dedicated about hands. It really helps getting a sense of how the human hands work and how remarkable they are. So we're trying to go with a design that is pretty accurate from an anatomical perspective. I think that will pay dividends in the long run.
So why mimic a real human hand? What's so bad about what we saw earlier?
This is the hand that we are currently using. It's pretty basic. There are a lot of actuator companies that are developing hands like this one because they developed the technology for building the actuators, which is this electric motor that you see in here. I don't even consider it a hand. One way to look at this is that yes, you have 5 fingers, but they have a limited number of joints. So for example, there are only 2 joints per finger, and what we say is that they are coupled, meaning if you close one, the other closes as well.
I see.
Okay?
So they look like a hand, but because they lack some features, they're a gripper.
Exactly.
Masquerading as a hand.
It's slightly better than the simplest gripper that you can have in a robot is a parallel gripper.
Right.
Exactly. This is just slightly better than that. It's like having 4 different grippers as opposed to a thumb. The good thing that they have in here is also this degree of freedom that makes it a bit better than a gripper, but it's very far from the dexterity that we expect a real hand to have, or a hand for a robot to have.
So what you're seeing now is an early mock-up Andrea and his team made to demonstrate tendons in action. Remember those motors we just saw in the old hand? Think of those like muscles. This hand, or gripper, only has 6 of them. But this hand over here, every string is like a tendon, and they're all attached to their own motors, or muscles. all 24 of them.
No, I think it's more complicated than people might think to control only one of the digits at a time.
Yeah.
The tendons do pulling, right? They don't
Correct.
do any pushing.
Correct. So it comes to, it's always a balance of forces. So we have in the back of the finger, there's a shared extension tendon. Actually, let's go to it's easier if we show it here. So we have a shared extension tendon that has the role of extending all three joints. It all comes down to a balance of forces between the flexion tendon and the extension tendon.
Okay, let's unpack what he said just a little bit. On our fingers, we have two main types of tendons. We have our flexor tendons that help pull our fingers forward, and we have our extension tendons, or extensor tendons, that help pull our fingers backwards. Now, the balance of forces comes with whether you're pulling more on the flexion side or more on the extension side. Flexion, extension, flexion, extension. Now when you add multiple tendons, that's how we can get our variable movement of each of the digits of the finger.
These joints are called DIP, PIP, and MCP. These are anatomical terms. For the strongest joint in the hand, which is the MCP, we want to either be able to pull both the flexion tendons and apply a lot of force, but if we pull them differentially, we get abduction, adduction, which is useful. For example, if you are grasping a spherical object, you gotta be able to like open and close your fingers relative to one another to have a stable grip, and it's something that the hand that we currently have cannot achieve.
As Andrea and I talked further, one thing became clear. Making robotic hands more human-like isn't about proving that we can, or even just because it's cool. It turns out that all the problems we're trying to solve, whether that be adding more dexterity to the fingers so they can hold odd shapes or small objects, or increasing the grip strength and stability, we find ourselves logically working back to solutions that nature's already come up with.
You worked with a medical facility to actually dissect or see the dissection of a human hand.
Yeah.
What was your reaction to that?
Yeah, so we had an opportunity to go see an anatomical study on a real hand. It really felt like this was some alien technology from a civilization that is like 1 billion years more advanced than we are. Then like there's a whole interesting other sort of like rabbit hole. We can make it maybe like do another video later. So we are developing tactile sensing. Now what we have here is just a mechanical sample, but we have some samples upstairs that can sense touch on the fingertip and the position at each of the joints.
Is a humanoid robot, and this is what's inside its head. You don't have to be a biologist or an engineer to know that this is probably not its brain. So what is it? And how does it help Phantom navigate the world? When building a humanoid robot, some things just make sense. You need at least 2 legs, 2 arms, and 2 hands to do what we do. However, our heads, like most animals, with their brain, ears, eyes, nose, and mouth, are made for sensing the world around us. But have you ever stopped to think why all those important parts are stuffed into a single exposed part of the body? What can we learn from that? Imagine you're in a large, dark room, so dark you can't see anything. Suddenly, a light turns on one side of the room. You're probably more likely to move that way, as opposed to away from what you can now see. This might be why animals started moving forward, and then more sensory organs became concentrated towards that one side. This common evolutionary trend towards having a head at all is called cephalization. The other trend that we can observe is that eyes tend to be as high up as they can get. This maximizes the horizon line, allowing us to see threats or food from a greater distance. That's a trait worth emulating, which is why Phantom has cameras on its head and not on its feet. But that still doesn't explain why our brains aren't safely tucked away in our chests like they are here on Phantom. That might be because our nerve impulses max out at around 120 meters per second. That's about 2.5 Roman Colosseums tall. But with electronics, a signal can travel at nearly 99% the speed of light, or 6,250,000 Roman Colosseums per second. With speeds that fast, there's no need to put the computer as close to the cameras as our brain might need to be to our eyes. Also in Phantom's head, we have IMU sensors to record velocity, orientation, and motion. All this together generates heat, and for those who have dissected any electronics before, you might recognize this piece, a heatsink. A heatsink's job is to drain the heat away from important components. Since we aren't using liquid cooling like the brain, this heatsink works by having a high thermal mass, or the property of a material to absorb and retain heat, which it then dissipates out into the air with the help of all that extra surface area. Add in a couple motors and you have yourself a Phantom head.
Not too many other pieces in there?
No, I think those are the main components on the head. So basically, movement is controlled by neck yaw, neck pitch actuators, and the cameras feeding into the microcontroller, feed back to the computer.
So with all these pieces put together, what does it actually look like to be in Phantom's head? What does Phantom actually see?